We'll get started. Sorry if you were looking for the recording. I forgot to post a link after downloading it or uploading it. Yeah, yesterday. I was busy grading your tests and I forgot to post the link until this morning for the, anyway, you were all here yesterday. Yeah. But it's there now. Yeah. So, all right. We are solving systems. And we'll finish up here with a couple examples. Kind of where we left off, kind of what I would call, say, the unusual cases. We saw one at the end of class yesterday where the two lines ended up being parallel lines. And if they're parallel lines, that's by definition, they never intersect, and so there's no solution there. And usually the equations are written in such a way that two different forms or something like that, so that it's not obvious just by looking at the equations to begin with that they are parallel. If you recall, if they were in the same, say, y equals mx plus b shape, we could notice that the slopes were the same slope. If they have the same slope, they're going to at least be parallel, and maybe, like we're going to see here in a minute, it could be the same line. If the same slope at different intercepts, then they're going to be parallel lines. But here we go. Here's an example for the other situation. And kind of like that I just said about the equations are usually presented in such a way that it's not obvious that there's something special about them. All right. So here are two equations. We are still talking about finishing up graphing to find the solutions here. All right, so we want to graph those two lines looking for that point of intersection. Now this first one is in our mx plus b shape. So I'm going to use the y-intercept of -6 to find a starting point there. And then I'm going to use my slope value of -3, and I'll think of it as -3/1. So I'll go over 1 and down 3 from that starting point that I know. Well, that's going to get me down a little lower, but over 1 and down 3 gets me a second point there for that line. And there's that. Okay. All right. Just check in, make sure I'm not going a little too fast yet. All right. I'll go too fast later. So I believe that would be the graph of that first equation. -6 intercept and slope of -3. Now,
can I do the next one?
Pardon?
Can I do this one? The 6x 2y1? So I believe we'd plug in the intercepts exactly. So 6 times 0 plus 2y equals -12 is going to become 2y equals -12. We're going to divide both sides by the 2, equaling y equals -6.
Okay.
And then do the same thing to the next one. It would be 6x plus 2 times 0 equals -12. Then it just becomes 6x equals -12. Divide both sides by 6, making x equals -2.
Okay, good. All right.
So we've got a point of 0 and 6, and 0 and -6, and -2 and 0.
All right. So now I'm going to have to whine and complain about my own first graph. These are obviously the intercepts, right? So 0, -6. Oh, look, there's that point. Happens to be one that we know is on the other line already. The other intercept is -2, 0. Well, I'm going to have to claim that my first line is a little crooked, but those are supposed to look like the same line. Right? I don't have the graph grid, so there's my excuse. But those are supposed to look like they were the same line. My dots are too big. There's my, whoops, there's my claim. If you are using your graph paper, maybe, excuse me, no problem. On your own graph paper, that might have looked better right to begin with. But those two, okay, does that work for you? Those two equations actually were different forms for the same line. Oops, gotta let a couple of people in here. Let's get them in there. Okay, so this should be what your situation looks like there if you were to try to graph both of those lines. Hello, folks who just showed up. I just noticed you, so welcome. Jump right in here. What I just did is graphed this system. Two different equations. I graphed the first one using the intercept and the slope and got that line. And we graphed the second one. It'll help us with the intercepts. And it turned out, when I plotted those intercepts and the line, it's the same line. And that's the point of this example. So they're the same line. Any point on the line would be a solution to the system, right? Any point satisfies them both. So there are an infinite number of solutions. And really, if we were trying to describe the set of solutions, what are all the possible solutions? Best we can do is actually present one of the relationships. Again, present one of the equations and say, well, if you want to find a solution, you gotta plot some points for that equation. You've got to plug some numbers in and find the ordered pairs if you were looking for specific solutions. Or if you want a solution for a specific x value, you'd have to plug that x value into one of the equations and find the y, find the ordered pairs. So the parallel situation had no solutions. That's just easy to say, right? No solutions. Here comes somebody else. Parallel lines, no solutions, and we would call these coincident. They are on top of each other, right? Lines have, well, that system has an infinite number of solutions, just like any line has an infinite number of solutions.
Okay, so you're saying that it has an infinite number of solutions, which is different from the solution of the system, which is specifically the math done to create those plot points? Is that what you're saying?
This system has an infinite number of solutions, basically because the system is only one equation.
And that line can go on forever, is basically what you're saying.
Yes, any line, unless we have some reason to chop it off, any line.
Okay, can you give us those terms one more time, please?
Pardon?
The terms that you just used, you said one was infinite, one was...
Oh, yeah, well, actually, I'm going to sort of classify now all three different types, okay?
Okay, great. Okay.
So, and let's see, so I have two graph grids. I'm going to sort of cheat here and draw a third graph grid here in the middle, okay? So I can show three different examples. Hopefully that will make sense. So let's say our most common situation is that we have two different lines, right? Two different lines, and they intersect in one point somewhere, and there will be one solution. The last situation I presented yesterday, two parallel lines, right? And they will have no solution because they never intersect. And then the one I just started with today, and here, I just try to show maybe double arrows, so it kind of looks like there's one line right on top of each other. The two equations represented the same line. So here are the three possibilities for these systems built out of two equations. So we have two sets of terms. Well, let's just say here, first of all, one solution, right? One solution, this one, no solutions. And this one, infinite number of solutions. Okay, now, kind of like, remember there were equations that were contradictions or equations that were identities. Remember there were words that sort of described those special situations for one equation in the last chapter. There's similar classification terms for our systems. The first one, the first term, and unfortunately oh well, you'll see. The first term has to do with, is there a solution? You know, I'll say that, you know. Is there a solution? And if there is a solution, we say that the system is consistent. So if there is at least one solution, we say the system is consistent. Yes, there is a solution. What's the negative of that? If there's no solution, it's inconsistent. That's the one that's like easier to remember, I think, because of the negative connotation, right? Inconsistent. This system is inconsistent. But that's the term. This one does have a solution. In fact, it's got 1 million of them or more. But so it is also consistent. This is a consistent system. We could find a solution. All right. The other term that's applied has to do with, qualitatively, you might say, are the lines separate from each other? Do they represent distinct separate lines? Well, those are separate. Separate or not, I might say here, okay? Separate or not? Are these two lines, not that they shouldn't touch, but are they distinct or separate lines? Yes, these are two different lines. Are they different lines? And the term we use is independent if they're separate. Independent. You might say they're not related to each other. They're independent. Well, these two lines are very separate, right? They are also independent. Independent, yeah. Well, those two are not independent. They're not separate from each other. But sort of the opposite of independent is dependent. So two different ways of thinking about them. And unfortunately, what I was kind of getting at is, oh, the one that's different, the inconsistent, isn't the same as the one that's different, the dependent. But if you can recognize that, oh, that one's the weird one, the different one, it's inconsistent. And that one's the weird one, it's dependent. Sometimes that'll just get you by as some places I have seen where they only ask you to decide whether it's inconsistent or dependent. Well, there are always these two conditions that you could use to describe them. Just very generally though, you want to understand one solution, no solutions, infinite solutions. And then if you're asked to apply one of these terms, then you have to think, is there a solution or not? Positive or negative? Is there a solution? Yes, it's consistent. No, it's inconsistent. Yes, it's consistent. Are they separate lines? Yes, they're independent. Yes, they're independent. No, they're dependent. There you go. That used to be like a standard test question for me in class. I draw these three graphs, maybe mix them up and provide the blanks and ask students to fill in the blanks. I don't see it quite presented in that form in MOM, but they're going to ask you some questions at least about how many solutions and maybe ask you to apply these terms. You'll see these terms in the end of section 5.1 if you're looking in your text. Okay.
I have a quick question.
Yes, please go ahead.
Are you the one creating problems for the math, like My Open Math homework assignments, or is it just kind of generated?
It's the course kind of has a template. I always go through and look for anything out of the ordinary that I'm not expecting, but basically, unless there was an issue, the template gets rolled over every term. In fact, all the Math 60 teachers might be using very much the same homework assignments for their classes. Now, the program itself generates an individual version for each one of you. It's like a coding thing where, you know, use this kind of number plus that kind of number and make it end up to be this kind of number. And then mom actually creates the same kind of problem with different numbers for all of you. So does that answer your question?
Yeah, that makes sense. I was just curious if you were the one kind of making the problems. If you
Well, I'm responsible.
Freedom.
You can blame me that I'm responsible for them, but I do go in, they are sort of a template that we've all kind of agreed, you know, to use.
Okay.
I can go in and change them too, you know, and I do that sometimes. I drop one here or there because I don't like that, something like that.
Okay, that's interesting. Thanks for answering that question.
Okay, oh yeah.
Yeah, Professor, thank you for breaking it down for us. And whoever asked that question, thank you as well.
Yeah, all right. So that really gets us through the ideas in 5.1 where we are graphing the equations and looking for the specific point. It's always, if there is a solution, well, those are special cases. If there is a solution here that's a single solution, it's an ordered pair. It's always X and Y. I'm already going to emphasize that. Sometimes you find a problem or you end up finding one of the values first, and we're going to have to go back and remember to find the other value. Now, some of you may decide to cheer at this point, but I'm going to take down the graph grids. Because now we're going to change gears and start looking for what I would call algebraic solutions, or ways to just manipulate the equations to find our solutions. Yeah, see if I can get this down without breaking anything. This is just a, see now I go down to the grocery store and say, okay, yes, can I buy this? There, enough of that for a few days. 5.2, that's what's happening now, okay? And let's see my papers. 5.2, solving systems by substitution. Okay. Now here's where I've said, we've already done this kind before. I'm going to make up something and not really try to finish it right now, but here's our rectangle problem, right? Remember the perimeter, 2 lengths plus 2 widths, right? And we would get some information like, oh, the total perimeter is, say, 20 feet. But then we need a relationship between the length and the width. The length is 3 more than twice the width. I might have come up with that relationship. The length is twice the width plus 3 more. That's a system of equations. 2 different conditions that have to work together in order for us to be able to find the values for both the length and the width. But we never bothered to really think of it early on, when we saw these earlier, as a separate equation. We just kind of like did this all in our head, and we replaced the L with that expression. And for this one, I just made up, the numbers would probably turn out weird, so I don't know if it's worth finishing it, but actually wouldn't be too bad, I think. Yeah, well, it'd be fractions. But here, notice the L was times 2, so I had to use the whole parenthesis thing, right? Parentheses times that whole expression. But there, I just did a substitution. I took this expression, which was supposedly equal to L, and I replaced the L in the other equation. I substituted it in. This is a big picture of what we're going to do in 5.2. In fact, I think there's maybe one, I know in 5.4, which is applications, we'll see this kind of problem specifically, and maybe there's one at the end of 5.2 like this, an application. They might have stuck one in. I looked at that this morning. But that's the concept in general, all right? So it's just sort of priming you there. we have already done some substitution, plugging one equation in a sense into the other. All right, so here I go with more specifics, okay? And looking for one of my better first examples here. All right, there's the system, 2 equations. All right, so kind of, I'm gonna make more or less an outline list of the steps. Hopefully we'll practice enough that it kind of makes sense anyway. We're gonna solve one equation. Here's my abbreviation for one of the variables. Solve one of the 2 equations for one of the variables. Kind of like in my first example there, I said L equals all that stuff. So it already was solved for L. Looking at these 2, oh, look at this one's already solved for Y. So the first step is going to be done for us in this problem. Second step, sub that expression from number 1 into the other equation. Now that's kind of abbreviating words here, right? Expression and equation, there's a couple of my abbreviations, but we're going to take whatever we came up with from this first step and substitute it into the other equation. This expression is telling me that Y equals this stuff. So now I'm going to substitute this stuff into the other equation instead of Y. So here, I'm going to just walk it through like that. Here's where I do my arrow thing again. So I'm going to take all of this and put it in there instead of a Y. X plus, I'll put parentheses in it for now because in situations where you might have to distribute, you're going to want those parentheses, but I don't really need those parentheses right now, but it helps to show what I did, I think, okay? So now I only have an equation that just has X's. Back to chapter 2, I can solve that. That's the third step. Solve that equation. All right, we're going to solve that equation now. So what do I get here? If you can visualize with me, there's no parentheses. I now have 4x's minus 2 equals 6. Add the 2. 4x equals 8. Divide by the 4. The x must be a 2. Okay, so I've solved that. The x that's going to work for those 2 has got to be a 2. And here's where 5 minutes ago I said, but we always have to find the other variable. Plug that value in. Plug that solution into one of the equations. One of the originals to find the other value. Run it out. I think you can almost see all that. So we're going to plug, I have to find the Y value, right? A solution is a point on a line. It's always an ordered pair. I need to find the Y that goes with it. So I need to go back up and plug it into either one of these. Pick one that you think looks easiest. This one is kind of solved for Y. That might be the easiest, or these are really small numbers anyway. So I could say, here's the X value, right? 2 plus Y equals 6. If I subtract the 2, the Y must be a 4. So I found that. Now, important, I got to write, I'll squeeze it in here and just say ordered pair, right? It was really unfortunate how many of you I saw, I thought I tried to repeat it over and over, didn't write your Y-intercept as an ordered pair on your test. you had the right number for that y value, but you didn't write 0, 2. I gave you partial credit. I knew what you were doing, but yeah, got to be careful. If it asks for an ordered pair, you got to write the ordered pair. There's our solution. Okay, write the ordered pair. Now you can always check, right? 2 plus 4 equals 6, or let's see, 3 times 2 is 6, minus 2 is the 4. Yes, it works in both equations, so you can always check if you've got the right solution. But there's my shopping list here for you. But, you know, we kind of walked it through. You get one of the variables solved alone so that you have this one variable is equal to everything else, and then you can take that everything else and put it into the other equation. That will be our process. I'll leave that up there to talk from, but I'll go on to another example, okay? And how about x plus 3y equals 10 and 4x plus y equals 18. Now that first one I did, it's kind of like the length already knew what we knew what the length was equal to something in terms of the width. This one, neither of the two equations is currently solved for just one of the variables. Yesterday at the start, I said, you're going to see this form a lot more often than we did in the last chapter. You know, x and y is on one side. So I have to do this first step. And you get to choose. I've got 4 different variables in this system. Which one do I think would be the easiest to get alone? Which one would be the easiest to solve for by itself? It's like, well, look, and these are what I would say the 2 first obvious choices. I could solve the first equation for an x by moving the y's without much difficulty, or I could solve this one for y by moving the x's. Equally, you know, doesn't matter. One's just as difficult as the other. I'm just going to choose this one arbitrarily. I'm going to solve this equation for x. Okay, I'm going to solve that one for x. Here I go. Here's where I do my arrow thing again. So hopefully you can follow me, and I won't have to show too many extra steps. I'm going to subtract the y's, and that's going to get me that x equals, I could say 10 minus 3y, doesn't matter, right? 10 minus 3y. Just make sure I didn't lose anybody yet, right? All I did is rearrange that first equation. But now this is telling me this expression is equivalent to the x value. So now I'm going to sub into the other, right? I'm going to sub this expression into the other equation instead of the x. So it's going to go there. Now I'm going to rewrite, do the actual substitution. Now I need 4 times all of that, so here's where I really do need the parentheses. Don't forget the rest of whatever is in that equation, right? Plus y. There's the big step. We did the substitution. Now I'm down to an equation that has only variables y, only one kind of variable in it, and we know how to solve that. I'll find the y value. I'll solve for y. So here I got to do my distributing. 40 minus 12y plus another y equals 18. 40 minus 11y, combining those y's, like terms. All right, so I'll subtract the 40 and leave the y's here, okay? So negative 11y is negative 22. 22 plus 18 is 40, yeah. And dividing by the negative 11 gets me that y equals 2, all right? Y equals 2. So there, solved that equation. I got all the way through step 3. Okay, just let you jump in if necessary. But now I have to find the other variable. I know the y value, I need to find the x value. Now, you can go back to any one of the equations that you developed from the originals. Like I could use the first one, I could use the second one, or this is the same as the first one. I could use this one if I wanted to, and it already tells me what x is going to be if I plug in the y over here. That's often a good choice because you've already done some of that work of rearranging. If it makes you confused at all, just go back and pick either one of the first ones. If that's okay, I'm going to use this one, okay? So I'm going to say, see if I can put it in here, okay? I don't want to make a mess. I don't want to make it difficult. Is my process here okay that I could erase this? If that's okay, I'm going to erase it and make myself some room right here. Okay, so I know that y is a 2. The x is going to be 10 minus 3 times 2. 10 minus 6 is 4. Ordered pair, my solution then. X first, then the y. There's my solution. 4 plus 3 times 2 is 6 is 10. Yeah, I could check. I could plug it into both. All right, I'm lingering. Any questions? But it's just going to keep going then. Keep doing more, okay? Practice. See if I can come up with one looks like, and then ask you guys to try it here, okay? Let you folks do it. And two x minus y equals 1. And somebody fell out, let it back in. And what's this one? Okay, y equals negative 3x minus 6. That's kind of like the very first one I did. It's already, this one's already solved for y. Why don't you give that a try, okay? Try this one on your own. I'm going to put all of this into there instead of y. Watch out for that negative sign. You do need parentheses. Anybody's confused, just shout out. I'll do a step. Just allow me to do, I'll do my circle thing. I'm going to put all of this in there instead of y. So we have lots of negative signs. Watch out for all those things. Good, yeah. Just, sorry not to distract you, but just to follow up on the question about, who makes up the problems. The answer is basically the same for the tests. We are encouraged to use the same tests so that all the Math 60 sections are being tested on the same test questions. We can make some adjustments, and I do that once in a while. But, and in particular, the final, we have to give the same final. Everybody gets the same final. I'm required to do that. But It's all right. I'm going to do the substitution step. Okay. I'm going to write one more step then. So here, this is going to be 2x minus negative 3x minus 6. So this is what I was talking about, all those. Got to have this negative, and you need those parentheses because now you have to distribute negative. Hope you got that. Anybody got an X value they want to give us? Not yet. That's okay. Something new. Okay, I'm going to do the distributing, okay? Did you get the minus on all of those? Yeah.
I got x equals -1.
I think that's what I got too. Everybody else? Everybody else, any problems? Any difficulties? Subtract the 6 and I get 5x is -5. Divide by the 5 and I get x is a -1. Hope that works for you. Let's put this over here. X equals -1. So now you need to find the y value. I would think using this second equation would make sense, as long as you're careful to say -3 times -1. But then all that work will tell you, give it the output y value. So what does that turn into? 3 minus 6. -3? Rattle, rattle. If I shake my head, rattle, rattle. All right. Please tell me if there was some point you got lost or confused about something, okay? But if that worked pretty well for you, I'm going to put up another one, kind of like my second example here, and ask you to try that one, okay? Good enough? Then 3, 2, 1. All right. Good, good. And yeah, good. Time. -x plus y equals 4. 4x minus y equals 2. Anybody who worked ahead to the next section might say, oh, there's a better way. Well, we'll get there tomorrow or Monday. All right. Here's one like the second example I did, where neither equation is solved for one of the variables yet. So you need to pick one of the variables to get all alone from one of the equations. The y might not be too hard here. The x, not very difficult, but just make sure you deal with the negative sign, or this one, the y, wouldn't be too hard to move. Like I might move the y over and move the 2 over or something. So maybe for the purpose of us all agreeing, would somebody like to volunteer or suggest one of the variables that we would all agree for the moment to try to solve for? Anybody want to pick one?
X.
You want, and if you say x, I would say this x, right? You're going to get this.
Correct, yeah.
Then we're going to get this x alone, and it has to be positive x, not negative x, okay? So if everyone will practice, let's solve this first equation for x. just like I said up there for that previous example. Rewrite that first one. Maybe it'll take you a couple steps because of that negative sign, okay? Let's rewrite that first one, x equals stuff, okay? If we choose the same variable, then we can talk about our steps together. Now I'm going to ask, just because we're having to do a few more steps here, let's check in on our expression here after you do that. All right, before you do the substitution, if that's, you'll allow me. Now, just because we like to leave it sort of like x equals and then everything after it, I'm going to leave the x and move the y to start. And you might have said negative y plus 4. I'll just say 4 minus y if I subtract the y's. Now I want positive x, so I'm going to multiply everything times negative 1, which flips all the signs. And so here is, or if you had it in the other order, one version or the other, that's what I think we're trying to come up with for the first equation. Okay. So now, from the first, you've always got to plug into the other equation. Otherwise, you're like just looping back into itself. You can't put it into the first one. You have to put it into the other one. This, now you want to, one version or the other, you're going to go put back up there instead of that x. And you need the parentheses, so you can do 4 times all that stuff. I'm going to rewrite that up there, and now I'm going to erase this and get out of the way so eventually we can show some work. So you're going to do that substitution and continue, okay? How you doing? I'm just kind of waiting, letting you do it, okay? Anybody get a y? What are we after, right? We're going to get a y value. Anybody have a y value yet? But 4 times.
I got positive 6 for y.
Good. All right. Then if you allow me, I'll finish up mine here then too. So here's my substitution. 4 times the y minus 4 minus the extra y is a 2. So here I get distribute 4y minus 16 minus another minus a y is 2. So 3y minus 16 is 2. Add the 16. 3y equals 18 and divide by the 3. Y equals 6. Ta-da, good for you. Okay. We found the y. Got to find the x. To go all the way back, either one of the beginning ones or again, I encourage you to consider using that one because it tells you what the X is right away as soon as you plug it in, right? X equals, we get 6. 6 minus 4, X is a 2. Write your order pair, get them in the right order. 2, 6 is that one point where those two lines would cross. All right. Good enough for that? Let's look at, whoa, I have time. Let's see. We won't finish another probably in 3 minutes. Should we stop there and then we'll pick it up? I'll review, I'll start again with a couple more variations of this on Monday. And so kind of refresh this topic. Now I do want to present one type. 5.1 and 5.2 have been assigned. We're supposed to try to have that done by Monday night. We'll see some work. We'll do some more work on Monday. I'm going to make up something, and it may not. I'm not going to try to solve it right now because if I make it up, it's gonna. Who knows how it'll turn out. Here's a system, right? 2 equations, and they're both solved for y already. Well, those y's still have to be equal to each other. This is kind of, I kind of use that word easy for this one. All of this stuff is going to go over there instead of a y, and you really just set the 2 equations kind of equal to each other. See what I did there? So that's a nice substitution situation. Something tells me maybe that's what the last problem in 5.2 is like. You get to write 2 mx plus b equations, and then you set them equal to each other like that, if I recall looking at that one. I looked at a bunch of stuff this morning. But now I could solve for the x pretty easily. Just because I made up the numbers, this one would be a fraction, so I'm not gonna try to do that. But that's how you would deal with that kind if you're giving them a try. Okay.
So at that point, when you have two problems that both equal y, you can just pick one.
I was a bit garbled. I think you were going to, what you're asking, you get the x, and then you can choose either one to find the y. Is that your question?
Well, yeah, I was just curious because normally what we're doing is we're plugging one equation in as an x or y value. So when we have 2 problems here that are both y, we're just picking one to plug in for y at this point, correct?
Well, you know, it kind of depends on which angle you're looking at it, but yeah, I took this and I plugged it in for y in the other equation. Right?
Is there a reason why you didn't do the other?
No, I mean, it just would have been switched order, right?
So it doesn't matter at that point. You just pick one.
Yeah.
Okay, thank you.
Which way do you want to go? Yeah. Right, I could have taken this one and started with 2x plus 5 equals the other one. Yeah, doesn't matter. Y is y. I'm not trying to make light of it. I hope that made sense. Okay. All right, folks, we'll give them a try. And of course, it's the weekend. You've got several days to send me questions. Please don't hesitate if you're working on something and you get stuck. Okay. All right, then have a nice weekend. It's supposed to be decent weather. And I'll see you on Monday.
Thank you.
Thanks, Professor.
Yes, you're welcome. See ya.
All right, thank you.